Okay, so hello, welcome to this conference and this talk. Thanks for coming out. Just a brief introduction. This is kind of about me in 3 sentences or less, and it's the only joke in this talk, so I'm glad somebody enjoyed it. So I'm a data scientist in Philadelphia. I work for a company called Cadent. We place bids on ad space for cable TV. So that's one of the main things that we do, and the data science team there, most of our work is around the bidding process. So a couple disclaimers about this talk, is it's mostly going to be useful for newer data scientists, but hopefully there's takeaways for everybody, and I'm going to oversimplify things, and some of the guidelines, examples I give aren't, they're meant to be illustrative and not comprehensive, and I'm kind of going for breadth and not depth, so if you have more in-depth questions, ask after the talk or come find me during the conference. It'd be great to talk about it. I'm going to go fast, and sometimes things that seem obvious need to be said out loud, as I've learned from experience. So I realized afterwards when I was looking at some of these slides, it was like, man, it's kind of obvious, but it does need to be said. So getting right into it, the goal of this talk is just to discuss guidelines and practices for robust model evaluation, especially model evaluation in industry, as opposed to evaluating models in a setting like Kaggle where you're trying to reach the top of the leaderboard. That's good, or evaluating a model or an algorithm so you can publish it. That's good too, we need those things. But this is more like inside of industry, how can you deploy with confidence because you've evaluated your model well. Another side goal would be too, to just talk about this more. I think this is a topic that could be covered a little bit better. Within this community, it's kind of the thing that you can really only get by talking to other people who are doing it, which is why conferences like this are great. So again, if anybody has any feedback, I'd love to hear it after this talk. I think it's a good conversation to have. So the outline is we're just going to briefly talk about the motivation for why we would want to talk about this. And then we'll kind of talk about evaluation throughout 3 segments of sort of product lifecycle or data science project lifecycle, which I'm just going to label before development, during development, and then deployment and beyond. So the motivation is all models are wrong. If you think about it, nearly every way that we formulate sort of the underlying ideas behind our models, we're admitting that the models are wrong. So we're minimizing a loss function, which is like choosing the least wrong model. We call our models an estimate, right? We have maximum likelihood estimations as a way of finding model parameters. We incorporate an error term, directly into the definition of our estimates. We talk about probability distribution over the model parameters, the things that we use to make a prediction. So fundamentally, we're always sort of subconsciously at least admitting that our models are wrong. But it's not just the theory that tells us that. This is what we do every day, right? And who's fit a model, and then checked its error on the data set and saw something like this. This is a wrong model. But this is what happens this is one of our worst days, right? On a better day, it looks like this. It's still wrong, but it looks better. But the key is, this might be something that we could actually use, which brings us to the well-known quote that all models are wrong, but some are useful. And that's kind of the key to this talk, right? Is we know that our models are wrong, but we can tolerate a little bit of error in production, right? We can tolerate a little bit of error in practice. But being able to discern, how much is too much, that's the key. And because we're at PyData, I'll call this the Zen of model evaluation. And I'll just break it into 4 points. All models are wrong, some are useful, others are not, and usefulness counts. And so we want to be able to distinguish between the some that are useful, the others that are not, and usefulness, the application, that's what really matters. We don't really care about what mean squared error is or categorical cross entropy if it doesn't add value to a product. So in healthcare, getting this wrong, could be measured with lives, or in advertising, the space I work in, it's measured in dollars. We need to get it right. So, kind of getting right into it now, before development, this phase is highly context specific, but it's essential for the rest of the project. If you don't start thinking about evaluation, how you're going to evaluate your model, during training and in production, before you start developing, it's probably too late. the rest of the project kind of, hinges on getting this right. And these are some of the obvious things that might need to be said out loud, but some of the hazards of getting this wrong is, your model doesn't actually solve the problem you're interested in, or it only indirectly solves it. You give the user something that's kind of awkward, and then they don't end up using it. It's not exactly giving them the answer that they wanted it. Or, you can't actually evaluate the model in production, which leads to reduced confidence in the model. Again, if users aren't using it, it's not useful, right? So, and if people don't have confidence in the model, why would they use it? So being able to sort of have a roadmap and keep this thing in mind from the very beginning is important, because you want to be able to prove that the model is helpful so that the users can benefit from it. Or you hit a point of diminishing returns. I think we could probably all raise our hands and say, yeah, I spent a lot of time, at least once in my life, constantly tweaking these hyperparameters of a model, and at the end of the day, it really didn't make a difference. If you kind of have some basic goals in mind, it can keep you from doing that. And future iterations could also be impaired if you don't get this right, and we'll talk about that a little bit later. So again, this is highly context specific, so some guidelines for this is just some things to think about in the before development phase. So think about framing the problem. I think I've realized that I've been doing this for about 4 years, and I think I've realized that one of the biggest value adds you can bring as a data scientist to a company is to help people who aren't data scientists frame the problems in a way that are suitable for machine learning. The things we do are somewhat unfamiliar to engineers and, product people and things like that, and that's great. We all specialize in our own things. So working together and helping to frame the problem in a way that, we can build a robust model and actually evaluate it. Some questions that you should be able to give clear answers to. How are we going to evaluate this model? How will success be measured? You should be able to give an answer such as, I'm going to improve some business objective by, some measurable quantity. And that could be, several different things. Again, is this more appropriate framed as a classification or regression problem? Seems obvious, but it's comes from experience that you really need to think that through. Choose your metrics and KPIs carefully. Some guidelines for that would be try to choose metrics that convert easily into business value or business terminology. So for example, mean absolute percent error is nice. It converts nicely into business terms. You can say, yeah, our predicted bid prices are within 5% of the winning bid price. And that's easy to disseminate that information among other teams. So when possible, try and do that. And comparability. Choose metrics that can be compared across time, across data sets, across iterations. You want to, not all metrics can do that, and so you want to make sure that what you're looking at is really comparing apples to apples. If you're going to roll out a new version of your model, you want to make sure that the criteria it's being evaluated on makes sense compared to the previous iteration. So think about deployment and future iterations before you start development. I worked with somebody who once said, nothing is more permanent than temporary, and I think that's a great quote. So prepare for deployment and future iteration. So for example, if you want to roll out your model, the next iteration using A/B testing or something like that, think about what sort of infrastructure requirements that has, what sort of requirements is that going to impose on your actual API. You'll probably need to be, if you're exposing your model behind a REST API, for example, you'll probably need to be passing back model ID or something like that so you can track the performance from one version of the model versus another. And think about the feedback loop. This is essential, right? I've worked on many, many projects in different industries where this is not as straightforward as you would like to think that it is. It's not always easy to tie the outcome to the model predictions for a variety of reasons. And there's a lot of subtleties here, but a couple of examples are ad recommendations. A user can't click on an ad that they weren't shown, so your model might predict across a bunch of ads, but if they're only shown one, they can only click one. If you don't think about this carefully, you may never be able to evaluate how maybe your second best predictions are doing in production. Or another example, suppose you work for a hospital and you have a model that's predicting if somebody's likely going to be readmitted to the hospital in the next 60 days. And the hospital goes and takes that prediction and people who are classified as yes, they will be back within the next 60 days. The hospital tries to do an intervention, some sort of measure to keep them from coming back. So the use case of the model is essentially trying to change the predicted label, right? So now you might end up asking yourself when you look at the results, is the model that bad or that good, right? Because you may have a lot of predictions and these people never came back. But maybe it was that good. You identified the people that were going to come back and the intervention prevented them from doing so, right? So again, these are things to think about in the end-to-end process. So this brings us to during development. This is probably the most generalizable phase. And I think it's a good opportunity, like amongst the team, to adopt and standardize best practices. I think I said in the abstract of this talk that like these things are better thought of as like a playbook than a rule book, but sometimes it is good to have sort of like a foundation of principles. So there's a couple other data scientists from Cadent here with me, and this is one of the things that we've tried to do is, within reason, define some best practices for how we'll evaluate models. So the first thing is test your assumptions, right? Garbage in, garbage out, we all know that. This is probably the thing that I am least inclined to do. I want to get a data set and fit it right away. But this is super important. If there's an issue with your data, there's going to be an issue with your model. Check the distributions of your data. Check the features, the ranges, the distributions, et cetera, against what other subject matter experts within your business, your industry, or company are saying about the data. If there's disparities between what you found and what people are saying you should find, be able to account for that. Maybe there's an issue with your ETL, or you need to revisit like the data understanding, the business understanding. But again, this is one of those things that, in terms of workflow, implement it early to keep you from wasting lots of cycles trying to get a model to fit to data that's not, that has some sort of fundamental issue. So just for example, recently I was working on a project and I came across something like this, where it was like a binary classification project. So I basically plotted the distribution separated by, the label 0 and the label 1 of a certain feature. And this feature I thought would be very useful for actually predicting the outcome. So I expected something like this. I expected the distributions of this feature to be very different depending on what class it belonged to. But in reality, it was something like this. They were nearly identical, which explains why I had trouble fitting the model. So this is something good to implement early. Again, test your assumptions. What I learned from this was, okay, I didn't quite understand the data the way that I thought I did. I need to go back and pull it again differently. Another thing that I think is very useful is to establish a baseline. So I would say like a good baseline is easy to implement, easy to understand, and it's simple, but it's not a straw man, right? So this should be, when I think of a baseline, it's like something that if you had to, you could probably deploy within a sprint. And you would be confident that it's working correctly. And this is just, your base performance. If any more complicated model can't, beat your baseline, then maybe you need to go back and revisit the data understanding, revisit the business understanding, or maybe you just don't have the resources you need to be able to solve the problem at that time, or you need to frame the problem differently. So some examples. A simple heuristic. So a concrete example of this is, I used to work in healthcare, and one of the models that we were interested in there was, if somebody had this disease last year, will he have it this year? And so, a heuristic for that is, there's lots of diseases and conditions that we know are chronic. So we could say, well, if this person had this condition last year, this chronic condition, we assume they have it this year. It's kind of on the borderline of that, like, simple but kind of a straw man, because it's not going to work for all the conditions, but it still kind of gets you in the ballpark of what you should expect a model to be able to beat. Another example is we predict ratings at Cadent. And so one of the things is, like, as just a simple heuristic to form a baseline is, well, let's just assume that like the ratings on cable aren't really changing much week over week. So let's use last week's rating and use that as our prediction. And to be honest, it's a pretty good baseline. to use because they actually don't change much week over week. There's things like seasonality where that approach will break down, but again, it gives you a ballpark of where you want to be. An interpretable model is another great example. So, something like a linear model, logistic regression, linear regression, something like a tree-based model where you could inspect the features. Again, just to give you an idea that you're on the right track. So another example, I won't really go into the details of this project, but I worked on a project and one feature kept shooting up to the top, and I couldn't explain why. It was unexpected. And then, come to find out that that feature was actually leaking information about the target variable, information that we wouldn't have at runtime. So, would have caused an issue if it was something that we deployed to production and was something we were able to catch early. So that's sort of another side benefit you can get from using an interpretable model. Another good example is like in the keynote, right? We saw just recently, the speaker took like these deep learning models and compared it against something like XGBoost, where most of us are probably familiar with, gradient boosted trees and that sort of thing. And again, it's a good baseline to say, there's a lot of like cost to deploying some of these deep learning models. Well, it should definitely be able to do better than something that's a little bit simpler if it's going to be worth the cost of putting into production. And it was, so that's good. It's reaffirming that, yes, this deep learning model is really worth the effort. If you have an existing model or methodology, some sort of business logic or heuristic that's already in production, obviously this is your baseline. And if you have an acceptance criteria, like this model, if the precision is less than 80% or whatever it may be, it's not going to be useful. That's like your baseline. And then, of course, you just choose like whichever one might be the best out of all of these, or whichever one you want to work with. Again, it's like a playbook, not a rule book here. So another topic that's useful to think about in terms of model evaluation is cross-validation, which is usually, when we see it, it's introduced as like k-fold cross-validation. We all kind of know how that works, right? It's like partition your data into, say, 10 sets, 10 partitions, and train on 9, test on 1, train on 9, test on 1. And that's good. One thing, though, that we found useful at Cadent is a form of cross-validation that sort of replicates the deployment pattern a little more closely. And this is something that looks a little bit more like backtesting, if you've seen that. If you've worked in finance or looked at like trading algorithms, that sort of thing. Basically what they'll do there is they'll go back and simulate how would my model have done in the market if I deployed it 6 months ago. And so we often do a similar thing here where to keep it really simple, let's say our deployment pattern is we're going to train on 1 month, predict on the next month, then train on that month, predict on the next. So your cross-validation could be like train on January, predict on February, train on February, predict on March. It's pretty easy to implement. It avoids leakage from future examples, right, into your cross-validation. The model's only ever able to see what happened in the past during train time, which is good. And it's more like what's going to happen in reality when you start training this model for production. Another useful example is sometimes it's worth training on a cleaner data set. So, if you have a data set that may be a little bit noisy or something like that, and you have an algorithm that, say, you're a little bit unfamiliar with, this is where I found this to be useful. You sort of want to separate that noise in the data set from the error that you see at train time. So to give a concrete example, again, I mentioned we predicted ratings, right, which could be formulated in terms of like time series. And deep learning's all the rage right now, right? So, the idea I had is, well, maybe we could use like an LSTM or a convolutional neural network or something like that, right, to solve this problem. It seems like something that we could try. So our team looked into this. One of the things I looked into in the beginning was, I didn't do this in the beginning. I wish I did. So what I did was we were really interested in predicting some sort of rating that only makes sense inside of our own internal Cadent, business structure, which is a little bit noisy. But we have access to national ratings, which is much cleaner. And The two data sets, though, are very analogous to one another. A lot of the same features are shared between the two data sets. So, I could try those approaches using a CNN or an LSTM or something like that on the national data set, something that I know is a little bit cleaner, that I know if I'm seeing all sorts of weird errors, it's probably I've implemented the model wrong or I need more regularization or something like that. And it's not just, yeah, this data is noisy, I didn't pull it correctly, I missed something, or, So yeah, that's it on that. Now we hit deployment and beyond. And again, this is what really matters, right? We really care about performance in production. And this is, there's a lot of things to say about this phase, but I guess I'll kind of talk about just two things in this talk. Is one, you really want to ensure that your model is useful and that it stays useful, and you want to be able to iterate with confidence. And so, of course, once you deploy a model to production, you're tying the predictions to the outcomes, and you're going to do some evaluations. But there are things, and that's like a no-brainer, and we're probably all doing that, and it's a good first step. Here's some other things that I think are useful in addition to that. So one is A/B testing. I'm not really going to go into a whole lot of details on A/B testing. I assume most people here are used to it or familiar with the idea. But this is a great pattern. So why would you want to do A/B testing? So let's assume this plot is like the model's error over time in production. And this red line represents a new release, right? So it kind of looks like the model's error has dropped since the new release. But has it really? Like, we're data scientists, right? Don't we want to give like a more like scientific answer as to just saying like, yeah, we looked at the plot and it dropped? Because who knows? Like, maybe it's going to rise up again in the future. You don't know. So A/B testing is like a great mechanism where you can deploy iteratively, send 5% of your traffic to the new model, 95% of the traffic to the existing model, and start doing comparisons. And eventually just ramp up the traffic that you're sending to the new model as you gain confidence in it, while you're performing these hypothesis tests, until eventually the new iteration is handling all of the traffic. And one other thing that I think is the last thing I'm going to mention is monitoring, which could cover a wide range of things, but some of the things that I think you would really want to think about monitoring is like monitoring the input data, looking for things like covariate shift and stuff like that, where the distribution of the data at runtime is different from the distribution of the data at train time. And that obviously is like a topic all in itself. Two useful guidelines that came from a paper on TensorFlow Extended, which is sort of like, put out by the TensorFlow developers. It's sort of like production, pipeline kind of infrastructure thing for TensorFlow models. As they said, keep it simple and keep it actionable. And I think this is useful, right? So an example they give is, like, if you're monitoring for deviations in runtime data from train time data, favor looking at ranges over something like Kullback-Leibler divergence, right? Like, if you look at, if you get a report and it says the KL divergence is greater than this or exceeded some threshold, like it's hard to understand that, and it's also hard to understand what the action you should take is. But if you get an alert that says, for this numeric feature, we saw values that are 5 times greater than the largest value we saw during training, that's a little bit more actionable. That's something that you can look into a little bit more often. You can monitor how many times those things happen. Or look, if you're receiving input from categorical variables and you're seeing new values that you never saw before, there may be legitimate reasons for that. Perhaps you have new vendors, new products, whatever. But maybe it's an indication that you need to retrain the model so that it can sync with the data that it's currently seeing at runtime. And another good thing that I think is a guideline to try and re-implement here is reuse any sanity checks that you looked at during development during this phase. So I actually had a slide on sanity checks and I removed it, but I would just say sanity checks, I think we were all doing them already. During training is, we're looking at feature importances or coefficients of the models, things like that, making sure they make sense. We're looking at the ranges say we're doing regression, we're looking at the ranges of what the model's predicting, making sure that we're not predicting things that are, way large, bigger than what we would really expect to see. And those sanity checks could be reintroduced sort of in the post-deployment phase where you can monitor for those things as well. So if you've already integrated them into your workflow during training, they're great things to carry over here. Maybe you can hand them off to QA or something like that, and those are things they can check for. And so that's it right now. So in conclusion, hopefully there are some takeaways. One of the things that I appreciate about these conferences is I think, there's a lot of opportunity to learn from other people who are doing this. And so hopefully you've learned something, and I would love for you to share your suggestions. This is definitely an area that I could grow in. I think the team I work with, we can all grow in. I think this industry can grow in. So, afterwards, I'd love to hear what sort of practices you guys have in development. And lastly, there's a link here in the slides, which I think the conference will link to. The conference will link to the slides, and the slides link to a blog post where I took basically the contents of this talk and I put it into a post, and it's on my blog, and there's a little bit more information there. So if you want more, that's where it is. And I guess now we can open up for questions.